right, so this is our second part of the tension and pulleys video. So I guess I should write part 2 on top. Tension and pulleys, part 2. All right, so for this video, so before we had a large mass being pulled over the edge of a table by a small mass using a pulley system. And we worked out the free body diagrams when there was no friction. Now in this video, I want to add in the effects of friction. So I want to imagine that there's some friction here. And then we will compare numbers here. I'll give you some masses and we'll use the previous formula and plug in, and you'll see that it behaves the way you expect it does. Okay, so we're going to go ahead and assume that the block starts out sliding. You could also do a similar problem where you figured out when motion was impending, sorry. Getting tired. So when the motion is impending. So we're going to assume that we have a kinetic situation. And we're going to further assume that the mass is sliding to the right, because depending on which way it's sliding, that determines minus signs on the friction forces. So right now we're going to assume that there's a velocity to the right. All right, so that's enough to have a well-defined problem. So let's go through and figure out what changes. Now look at well, first off, let's do the small mass. The small mass only knows about forces that directly talk to it. Well, friction's way over here on the large mass, so the small mass won't change, or won't know anything about friction. So therefore, this free body diagram looks exactly the same. Copy, paste. For the large mass object, in the vertical direction, friction doesn't do anything. Friction only acts in the horizontal direction. Where friction comes in is along the surface. We now have F sub k, friction force, pulling it backwards. And if you're asking, how did I know that the friction force is going that way? Well, friction opposes velocity. So if the block is moving to the right, the friction is to the left. If I had done a different problem where the block started out moving to the left, say you'd given it an initial push, then friction would have been going to the right. So you have to read the problem carefully and set it up in an appropriate way. All right, because the free body diagrams are so similar to before, I can directly write down the formula for the net force for the small mass, and I can handle the y component of the large mass free body diagram, and then all I have to do is focus on the horizontal bits. Okay, so for the vertical direction, for the small mass, the net force formula is going to say that the tension minus little m times g equals little m times the acceleration of the little mass. That's what we found in the last video. Or I'm just finding the net force from the diagram and setting equal to mass times acceleration. The other thing we found in the last video, or just because it's not accelerating at all in the vertical direction for the large mass, is that the normal force must equal the big mass times g. And the thing that's really useful about that is then I can immediately say that the friction force will have a magnitude equal to mu sub k. Say it with me now. Mu sub k. It's never, ever, ever mu sub k. We are not farm animals, okay? Mu sub k, not mu sub k. Be civilized. All right. Anyway, the kinetic friction force is mu k times the magnitude of the normal force. Mu k times the magnitude of the normal force. All right, now I can focus on the new part to this problem. Before, the only force acting on the large mass in the horizontal direction was tension. Now there's also a negative friction component. So I can say that T minus the friction force, but over here I found that the friction force was mu sub k times the normal. So that's T minus mu sub k times the normal. I'm going to drop the magnitude symbol because we know it's positive. Normal force points. The symbol N represents a positive force which goes up. And because N equals mg, I can go ahead and write that as capital M times g, just substituting in. So tension minus mu sub k times m times g equals capital M times the acceleration of the large mass. Now, these objects are still tied together, and just like in the last video, we found that the accelerations have to be equal in magnitude, they just differ by a minus sign. So when the large mass moves in a positive direction, the small mass moves in a negative direction. So I can just replace this with minus the acceleration for the small mass. So I'm going to circle my key equations at this point. Okay, that's it. There's no more physics. We're done. Now it's just arithmetic. So how can we solve this? So I have two equations and two unknowns. I had that last time, but this extra term makes it a little bit more fun. So you know what I would do? If I took the top equation and I looked at the top equation minus the bottom equation, look what happens. The tensions, the two T's would cancel, and I would get this weight term minus a negative friction term. And I would, on the other right-hand side, I'd have small mass times acceleration plus, it'd be a double negative, plus large mass times acceleration, and I could factor that. So that's what I'm going to do. I'm going to name these things. Let's name this heart and square. And I'm going to work out heart minus square. I don't know what else to call it, so that's what we're going to do. Heart minus square. So I take the top line minus the bottom line, and that gives me minus little mg plus mu k capital M times g equals little m plus big M times the acceleration. And again, if we had messed up this minus sign on the acceleration, we would have had a minus sign there. And then we could just rearrange this thing. And so we get the acceleration equals minus M minus mu k big M all times g divided by little m plus big M. Okay, I know I'm running out of space there, but hopefully you can all see that. Now I regrouped it this way, basically because it mimics what we found last time. Last time we had the following formula, that the acceleration with no friction, so there's no friction here, then we found the acceleration was minus little m g over big M plus little m. Okay. Now, well, look, what does friction do? Friction impedes motion. It's like throwing on the brakes. So look at the magnitude. Look at the effect of the friction term. The mu only appears right here in this expression, and the effect is it mimics a reduction of the mass in the numerator. All that being said, it's kind of like you had a smaller weight pulling down. So it effectively will cause the acceleration to be smaller. So the friction force is reducing the acceleration. I promised you some numbers, so let's make up some numbers, but we're going to use these formulas now. Having derived them symbolically, we're not going to re-derive the whole problem with numbers. The whole point was just to get to that place. So I'm just going to give you some numbers and we'll calculate this. But we can already, if you're following the algebra, you can already see the desired result. The friction causes it to fall more slowly. Let's set some masses here. Let's say that big M equals 3 kilograms. And let's say little m equals 1 kilogram. And let's say mu sub k equals 0.2. Okay, so plugging in these numbers, we find without friction, we get an acceleration of minus 1 times 9.81 divided by 4. So this would tell me when there's no friction, the acceleration equals, typing in numbers, I get negative 2.45. Whereas if there is friction, so with friction, I do the same basic thing, but I get a different number. So I get 1 minus 0.2 times 3 times 9.81 divided by 4. And I get an acceleration of, I get an acceleration of negative 0.981. And I should put in my units here. This would be meter per second squared, meter per second squared. Notice there's an interesting thing, and actually you guys saw this in lab way back when we were trying to set up motion where something would slide when at a constant velocity, or when the acceleration would be 0. Notice if you adjust things so that the small mass minus the friction coefficient times the large mass equals 0, the acceleration in this situation would have been 0, and it would travel at a constant velocity. And if you continue to make the large mass be bigger and bigger and bigger, eventually the acceleration would reverse sign, and the falling mass would actually slow rather than speed up as it fell down. And it all has to do with the magnitudes of numbers when you plug in. Okay, sorry for the length of it and all the little details, but hopefully that gives you an idea how to solve problems where you use ropes and pulleys and you use Newton's laws to kind of pull multiple things together. Just an observation. When different objects are tied together with a rope, there's going to be some sort of constraint relating their motions. Their accelerations are going to be the same, their velocities are going to be the same, so there's going to be some sort of statement like that. Okay, see you next time.